the worksheet with the point charge at the center and the equipotential lines that went around it, right? And we talked about the potential at point A versus the potential at point B. And anywhere on that blue line, you're at the same potential. Anywhere at the red line, you're at the same potential. But you were at a higher potential at point A than you were at point B. I think we went through that, right? Yeah, all these. The electric field was greater at capital A, less at capital B, things like that, right? The potential. Talked about potential differences on that worksheet. And then we said that from a charge, if we have a potential being caused by a positive charge, some distance away from a positive charge, the potential is given by kq over r, right? Electric potential from a point charge. And if q, in this case, you must use the proper sign for the charge, q. So if that's a positive charge that's causing that potential, then we put a positive q in there. We get a positive value, like I've drawn it here, a positive value for q, some distance r away from the point charge. A positive charge is repelled, right? Positives repel each other. A positive charge is repelled by the positive that's creating this potential, and so it would go toward lower potential. A positive charge wants to roll downhill, wants to go towards lower electric potential. Because why? Because that's how it would move to lower its potential energy. Just like dropping a pen, it wants to go to its lowest point. The force of gravity acts on it, and it goes to lower potential energy, and its kinetic energy increases, right, as it does that. Same here. You let go of a positive charge in front of a big positive charge, it's going to start moving away. Its kinetic energy goes up, its electric potential energy goes down. You could think of those two charges kind of like a spring. Pushing those two positive charges together is like compressing a spring, right? There's a lot of stored energy in there. You let go of the spring, it springs back to its natural length. You let go of those two positive charges, they shoot apart. It's got energy stored because you've pushed them together. They don't want to be together, right? So there's stored energy there. Electric potential energy. You let go of them, this positive charge moves away from the other positive charge. Its kinetic energy increases, its electric potential energy decreases, and it moves to a position of lower potential. So for a negative charge sitting in front of a big positive charge, exactly the opposite is true. A negative charge, we say it wants to roll uphill. It wants to go to higher potential, the electric potential, because that's where it has lower potential energy, because the minus sign switches everything. So I wrote it over here. The change in potential energy, electric potential energy, is the charge times delta V. And so for a positive charge, delta V is going to be negative, the Q is positive, and so we get a negative change in potential energy, right? It goes down. It goes to a position of lower potential energy. And for a negative charge, the same thing. We want to figure out the same thing here. In this case, delta V is positive, right? It goes to a higher potential, so delta V is positive, but Q is negative, so we get a negative change in potential energy, which is what we want, right? We want the particle to go naturally to a position of lower potential energy. Just like when you drop something in a gravitational field, it always goes down to a position of lower potential energy. Same with electric charges. They always move on their own to a position of lower potential energy. And so that's why it works out nicely delta V is positive, Q is negative, we get a negative change in potential energy. Here they switch, but we still must get that negative change in potential energy. So you want to kind of get in the habit of thinking, what direction would this particle go on its own? Would it wants to get away from that positive charge, it would move to the right, and kind of reason through the process that way. A few ways of thinking about this. The electric field points in the direction of decreasing potential. The electric field points in the direction of decreasing potential. So the electric field from a positive charge points in this direction. So as we move away, draw it in blue, the electric field points to the right from that positive charge as we move out. So as we move in that direction, the electric potential must go down. And then we can flip it all around. A big negative charge fills the space around it with an electric field, and we can say that there's some electric potential at given points in space, and we can plot it. And in this case, it's still kq over r, right? We're still looking at the electric potential around a point charge, so we still use kq over r, but q is negative this time. So it flips it. And let's do our little test. What direction does the electric field point? Electric field. Electric field points toward a negative charge. And that means that as we get closer to that negative charge, the electric potential has to go down. The electric field points the direction a positive charge would go if we let go of a positive charge, right? So a positive charge would go toward it. A positive charge wants to go toward lower potential, down the potential hill. A negative charge would want to go to the right or up the potential hill. So it all works out in the end. But make sure you can think through it so that it makes sense to you.